All right, let's just jump right in. We've all heard this idea, right? This really beautiful, kind of romantic notion that the universe is woven from these invisible fields, this grand cosmic tapestry that makes up everything we see and touch. It's a really powerful image. But what if it's just that, an image? What if the very foundation of how we think about this is more of a mathematical convenience than an actual physical fact?
And you see this concept everywhere. It suggests that fields are the literal substance of reality. And look, it's an elegant, super compelling story that has totally captured our imagination. But today, we're going to pull at one of the main threads of that tapestry and, well, let's just see if it holds up.
And this gets us to the absolute core question we're exploring. Physicists use maps, these are their mathematical models, to describe the universe. But have we become so mesmerized by how beautiful and elegant our maps are that we've started to mistake them for the actual territory itself? That's the conflict we are digging into right now.
So our first big point is all about this distinction. The central argument here is that when we get our mathematical frameworks confused with actual physical stuff, we don't just get our philosophy wrong. We actually stop ourselves from making real scientific progress. It's a subtle mistake, but a really profound one.
This right here, this is the heart of the problem. The argument is that our current models are kind of like a shadow on the wall. They do a great job describing the shape of reality, they can predict its movements, for sure, but they are not the thing that's casting the shadow. We've basically fallen in love with the shadow, not the substance.
Now, to really wrap your head around this, you have to understand that the whole problem kind of starts because the word field is being used to mean two completely different things. You've got the tool, and then you've got the thing the tool is supposed to be describing. In physics today, when a scientist says field, they're mostly talking about a mathematical object. Think of it like a super sophisticated spreadsheet that's laid out over the entire universe. At every single point in space, we just assign a set of numbers. Maybe they represent strength or direction. It's incredibly useful for doing calculations, but notice what it's not. It's not a thing. It's just a description. And this table just lays out the disconnect perfectly. On the left, you've got the mathematical model. It's abstract. It's just numbers assigned to coordinates, basically a description of a state. But on the right, you have what physical reality actually seems to require, a real substantive medium with its own built-in properties, like stiffness or tension, a continuous fabric that literally holds itself together. The model is a list of data points. Reality has to be a fabric.
So if this mathematical field is just a kind of toy model, where exactly does it break down? Well, this analysis points to three very specific, really critical failures that basically prevent it from ever being the real fabric of reality.
We're going to walk through each one of these. First, this fundamental problem with using numbers as a foundation. Second, the fact that the model has no glue holding it all together. And third, its complete and utter lack of any physical mechanical properties.
Okay, let's start with the number problem. It's a subtle critique, but it's a devastating one. Our model defines a field by assigning numbers to points in space. But think about it. What is a number in a physical sense? It's an abstraction, right? It's a tool we use to measure a property. It isn't the property itself. Saying a field is numbers is like saying your height is the number 6, instead of a physical property that can be measured as 6 feet.
This quote just hits the nail on the head. If the field is nothing more than a collection of numbers, then what are the numbers actually measuring? See, according to this critique, the model gives us the measurement but completely forgets to define the thing that's being measured. It's like having a ruler with nothing to measure.
All right, on to the second flaw, the connectivity gap. In the math model, every single point in space is its own isolated island of data. There's a value here and a value right next to it, but there's no built-in physical reason why they should have any influence on each other. The equations have no glue that makes the fabric continuous.
And the consequences of this are actually huge. The model just assumes space is continuous. It doesn't explain what holds it together. And that means it can't explain why a ripple in the field at one point should travel to the point next to it. It can describe the wave after it happens, sure, but it can't model the physical transmission itself. It's like the model sees the dominoes fall, but it has no concept of one domino actually hitting the next.
And this leads us to the third flaw, which is maybe the easiest one to grasp. A real fabric, you can stretch it, it can resist being pulled, it can vibrate, it has actual mechanical properties. The mathematical field, since it's just a collection of numbers, has none of that. It is, for all intents and purposes, a ghost.
So the crucial point here is that two key properties are totally missing. First up, elasticity. Real things can store and release energy when you deform them. That's literally how interactions happen. Second, resistance, or what physicists call a modulus. This is really just a fancy word for material stiffness.
Without some kind of stiffness, a field couldn't even support waves. It would just collapse, or offer no resistance at all, meaning things could travel infinitely fast. A real fabric needs both stretch and tension. Our model has neither.
So, okay, after tearing all of that down, what's the alternative? How do we get from this mathematical shadow to something that actually feels like a real physical substance? Well, the cool thing is, this analysis doesn't just criticize, it actually points a way forward. The path forward really boils down to 3 essential steps. First, we have to stop using numbers as the foundation, and instead define the physical thing our numbers are supposed to be measuring. Second, we have to build the mechanism for physical connection, that glue, directly into the model. And third, properties like elasticity and resistance can't just be afterthoughts. They have to be fundamental, core attributes of the field itself.
So, where does all this leave us? Well, it suggests that while our current physics is unbelievably powerful for making predictions, it might be fundamentally incomplete in its description of reality. We might just be experts at describing a shadow on a cave wall.
This final quote just sums up the whole argument perfectly. The real fabric of reality, a medium that resists and connects and behaves like a physical thing, it's out there. And our current mathematical tools, these fields we use, they're just pale, brief descriptions of it. They aren't the thing itself.
And that leaves us with a really provocative question for the future, doesn't it? We have become absolute masters at calculating the behavior of the shadow. But what new ideas, what new kind of physics is it going to take for us to finally turn around and see the true substance of reality that's casting it?